Good morning, friends. The learning objectives of today's lecture is to understand electronic ignition system. Now, the first system is called as a transistor assisted control system, which is called as a TCI, or we are calling it as a transistorized coil ignition system. In automotive application, the transistorized coil ignition system, which provide a higher output voltage and use electronic triggering to maintain the required timing, are fast replacing the conventional ignition system. This system are also called as high energy electronic ignition system. So the advantages of this system, that the reduced ignition system maintenance, reduced wear of components, increased reliability, extended spark life, improved ignition lean mixture. Now the circuit diagram as shown here. Here you can see that the contact breaker, primary winding, secondary winding, distributor, ballast resistance, HT cable, spark plug, cam, battery ignition switch is also provided over here. Now here we found that the contact breaker and the cam assembly of conventional ignition system are replaced by the magnetic pulse generating the system, which detects the distributor shaft position and send the electronic pulse to the electronic control module. The module switch off the flow of current to primary coil, inducing a high voltage in secondary winding, which is distributed to spark plug as in conventional breaker system. The control module contains timing circuit, which later close the primary circuit so that the build-up of primary circuit can occur for next cycle. There are many types of pulse generator that could be trigger the electronic circuit of ignition system. A magnetic pulse generator, where a gear shaped iron rotor driven by a distributor shaft rotates past the pole of stationary magnetic pickup, is generally used. The number of teeth of rotor is equal to the number of cylinder. The magnetic field is provided by a permanent magnet. As each rotor tooth passes the magnet pole, it first increases and then decreases the magnetic field strength. Now the pickup coil wound on the magnet producing the voltage, and in response of this the electronic module switch off the primary circuit coil current to produce the spark as rotor tooth passes the alignment and pick up the coil voltage here. Now the increase in position of the voltage waveform after this voltage reversal is used by the electronic module to establish at this point. Now the primary coil current is switched on for next generation of the pulse over here. So this is related with the TCI. Now here you can see that again distributor, then spark plug. The distributor that gives the sparking position inside the cylinder, piston cylinder arrangement. Now the next system, that is the high voltage capacitive discharge ignition system, which is also called as CDI, or we are saying it as a capacitive discharge ignition system. The detailed diagram is shown over here. In this system, a capacitor rather than the induction coil is used to store the ignition energy. The capacitance and the charging voltage of capacitor determine the amount of storage energy. ignition transformer step up primary voltage generated at the time of spark by the discharge of capacitor through the this thyristor you can see over here, and to voltage required at the spark plug. The CDI trigger the box contains the capacitor. Now you can see the trigger box over the SCR triggering box we are providing, then DC to DC converter we are providing, then distributor is provided, HT coil is providing, SCR circuit is providing. Now here you are finding that the charging device which is converted the battery voltage to the charging voltage by means of pulse via the voltage transformation, the pulse shaping unit and the control unit. The advantage of using this system is that it is intensive to electronic shunt resulting from spark plug fouling. Because of the fast capacitive discharge, the spark is strong but short, which led the ignition failure due to lean mixture operating condition. This is main disadvantage of this CDI system. Now the next point we are going to discuss, that is the engine starting system. For engine to start, its crankshaft needed to be rotated to achieve certain speed by overcoming the static inertia of various parts which rotate, reciprocate or rub against each other when engine runs. So to do this, some device is required to crank the engine to provide adequate torque and sufficient power. This device should be able to draw power from some captive equipment moving with the engine. Starting system are generally by kick starting in small two-wheeler, by electric motor in heavy two-wheeler, and in also four-wheeler, by air motor in tanks using the air compressor. Requirements of the engine starting system. The condition of an engine at the time of starting are not conducive for initiation of the combustion, since the temperature of cylinder are too low. Further, at low speed, the time required to complete the suction and the compression stroke are relatively higher, due to which heat transfer from the working substance are high, therefore further lowers the temperature of working fluid during the compression stroke. Therefore the temperature and the pressure are not sufficient to initiate the combustion. In addition, if the speed are low, the unavoidable leaks pass the piston rings, and likely leaks the inlet and exhaust valve would further lower the pressure and temperature during its compression stroke. The cumulative effect is that the pressure temperature are not sufficient to ignite the fuel which is to be injected at the end of the compression in case of CI engine. Similarly, suppose we are going to discuss in case of the SI engine. In case of SI engine, for spark given to the engine to initiate the combustion with inadequate flame speed, therefore there is certain minimum speed at which engine must run before engine can start firing. The required speed depends upon the atmospheric condition, type and the size of the engine. So that's why we are saying that for the engine to start, cranking speed should be adequate around the 100 rpm. Sufficient torque is required to crank the engine, which may be 10 to 30 Newton meter in case of the small engines and 50 to 150 Newton meter for the heavier engines. Cranking ratio between a motor and the flywheel should be such that minimum torque is required to crank the engine, generally 15:1. In case of the starter, it is required to rotate 1500 rpm to crank the engine at 100 rpm. So the power required should be adequate to meet the heavy requirements of the energy. So that's why these are the requirements of the engine starting system. Now this circuit shows the starting circuit, means here we are saying that this is the electrical starting. In this system, these systems are used commonly for small capacity petrol and diesel engines. Now the basic system consists of a battery, starting switch, starting motor and solenoid drive mechanism. The battery supplies the energy to the starting motor through the starter switch. Starting motor are series wound motors designed to operate on large current at low voltage. The motors draws large current at slow speed and small currents at large speed. Usually half of the brushes are ground to the frame and the other half are connected to the field coil. Starting motors used for large engines used 4-field winding and 4 poles to develop large torque. The current from the battery is led to the commutator of the armature through the field coils and through the insulated brushes. The current in the armature creates simultaneously 4 poles are adjacent to the 4 fields of the poles to produce attractive and repulsive forces that turns the armature. So this happens in the this starting motor, and the starting motors are linked to the engine to the engine flywheel through the gears and supplies the torque till the engine starts, and then to be disengaged from it automatically when the engine is running. A pinion gear is attached to the starter armature drives. A large gear is attached to the flywheel of the engine when engine is being cranked. Motor speed reduction to the engine speed in the gear ratio is 8 to 10, and the starting motor torque to the engine is increased by the same ratio. Two general methods engaging of starting pinion with the flywheels gears are used. One is the Bendix Drive and other is the overrunning clutch drive. Now a solenoid is introduced in the circuit to assure positive engagement of the starting motor pinion with the flywheel until the engine is started. When the current is passed to electromagnet winding, it attracts the soft iron core called the plunger, which operate the pinion by shifting the lever. When the circuit is broken by releasing the starter switch, the magnetic field is broken, and this action is also forces the plunger out and disengage the pinion while with the flywheel. Now here you can see some of the actual pictorial views of the starter motors. Now this figure gives you the clear idea about the how the what are the components and how these are the located. You can clearly see over here the front view and the side view of the electrical starter. Here you can see the solenoid, then you can see the bushing is provided, and the auxiliary parts such as a piston stop, return spring, then the spiral spine, assistance spring, field coil. Now the main component is the armature, you can see, then the brushes, bushing, which we have discussed earlier, then the cumulative, then the plunger. So all these parts are shown over here in this diagram. So just we are going to rewind these points again. Starting drive. For starting the engine is required to be cranked at around 100 rpm. If motor rotates at the 1500 rpm with a drive ratio of the 15:1, engine will be cranked at the 100 rpm. But when the engine starts and if starter pinion is still in mesh with the ring gear on a flywheel, the engines will rotate the armature shaft of the starter motor at very high speed. With the results, the cumulative segments and starter winding will fly away due to centrifugal force. Therefore, it is necessary to have such a device that has been started, and starter pinion should be disengaged from the flywheel ring gear immediately. Also talking, we have seen the starting motor. Starter motor is driven by the current drawn from the battery. It is mounted on the side of the engine near the flywheel. Motor has to be powerful enough to crank the engine, and starting motor is similar to the DC motor. It requires to develop about 10 to 30 Newton meter torque for smaller engines and 50 to 150 Newton meter for heavier engine. Motor may be series wound or series shunt wound. Starter motor draws heavy current as 500 ampere. As motor draws very heavy current, battery voltage falls very sharply, and drive ratio is around 15:1 may be required, but largely it shall depend upon the size of the flywheel. Motor pinion should be disengaged and as once the engine starts. Now we are going to discuss a Bendix drive. Now you can see in this figure, in the Bendix drive is the inertia type drive. Here you can see the starter motor, collar, armature shaft, then threaded sleeve, flywheel, fixed driving head, then torsion spring, sliding dock, unbalanced weight, pinion, and the collar. Now in the Bendix drive is the inertia type drive in which starter pinion is made to engage or disengage with ring gear. There is a threaded sleeve on the armature shaft which can slide and turn freely over the shaft. So shaft is keyed to fixed drive head which is connected torsionally to sleeve by a coil spring which takes up shock of the engagement. An unbalanced weight is attached to a pinion to prevent its rotation on the sleeve thread. Now when the motor starts, the armature shaft rotates, and because the pinion cannot rotate due to the unbalanced weight, it moves axially towards the motor till it is engaged with flywheel. Further movement of the pinion is prevented by the collar attached to the sleeve, and because of this the pinion starts rotating. Since the pinion is in mesh with the flywheel, it is rotated and the engine start. When the engine start, flywheel now rotates and the pinion much faster than the armature, so the starter switch off. With the results, the pinion is backed out and mesh with the flywheel. So this is related with the Bendix drive. So this is related with the today's lecture. So in today's lecture we have discussed the various types of the electrical starting methods. Also we have discussed the TCI methods, that is the electronic systems we have discussed. Then we have discussed that the how Bendix Drive also. And in the next lecture we are going to be discuss what are the engine emissions, and or what kind of the knobs related with that engine emissions. So thank you.